let's talk about the 555 timer. Why is it named that way? What is it used for? And some technical details regarding the timer chip. So we'll begin with the purpose. Why do we need this? So the first question is purpose. Well, the purpose of this chip could be manifold. So there are primarily two configurations that we will run this chip in. They are the A-stable mode, which is essentially explored in experiment 7, and there's a monostable mode, which is part of project 3. The A-stable mode allows you to generate a timing signal, hence the name timer. So it's essentially a clock input that you can generate using an IC for a particular frequency and duty cycle. So whatever you desire in terms of frequency of the output square wave and duty cycle, you can generate that from this chip by doing some design, and we'll talk about what that design looks like today. So that's as far as A-stable mode. So allows you to generate a free running square wave for a given frequency and duty cycle. Um, the monostable mode has a slightly different purpose. So monostable mode allows you to generate a clean pulse. So just one pulse as opposed to a free running oscillator. Um, so this could be like in a scenario where you are trying to look at a switch bounce or switch debounce, that might play a role in that. So we'll try to explore the switch debouncer in project 3, but for now the main difference between these two modes is monostable mode allows you to generate just one clean pulse when a certain event happens for and the design over here has to do with for how long will that pulse be high. And for the A-stable mode in experiment 7, we'll be focusing on a free running oscillator, a square wave, such as the clock over here. So those are your two modes. And those two modes are essentially, you go from one mode to the other by changing the circuitry around the chip. So it's the same chip, but the circuitry around that chip is going to dictate what mode you operate it in. Okay, so that's the purpose. Let's see here. So in order to understand the timer chip very well, we need to do item number 2 and 3 on this slide, which is the internal circuitry of the timer chip and the external connections that you make to design the astable or the monostable timer for a desired output. So we'll start with the first one in order to help us with the second and the third, the charging and discharging of a capacitor. So let's look at that on a new slide here. And let's say we have charging of the capacitor here. So I'll just say charge cycle. So for this, I'm going to assume that I have a voltage source, a DC voltage source will do, and I have, say, a switch, and I have a resistor, and I have a capacitor here. And this is ground. I have R over here. Let's say I have a capacitor over here. I'm providing this circuit with some input voltage, and I'm measuring the output voltage across the capacitor. So this is my V out. And this is a switch here that can close at some time, say t0 at 0. So Initially, the resistor and capacitor are not connected with the voltage source, but at time zero, when my analysis begins, I'm going to close the switch. So when I close the switch at time zero, what is going to happen to the capacitor? Well, the capacitor, if I assume that initially capacitor has no charge, assume no charge in capacitor at the beginning at t equals 0. So I'm assuming that there's no initial charge on that capacitor, and at time t0 I have started charging that capacitor by applying a voltage of V in across it, but through a resistor R. So what is going to happen? Well, we need to go through an analysis of this circuit which relies on solving differential equations. As you know, the current through the capacitor, say I, is going to be C dV by dt. So it's a differential entity, and that combined with Kirchhoff voltage law for this particular loop will result in a differential equation that you can solve using the initial conditions that have been mentioned. So that's a pretty intense process, which we are not going to look at all those details for this class. It is part of electric circuits. We don't look at that all those details in EI. However, we can take a look at the solution. The solution here, once we do this differential equation and solve the differential equation and substitute the initial conditions, we can substitute for V out. So it turns out that V out, which is the voltage across the capacitor as a function of time during the charge cycle, is going to be V in multiplied by 1 minus e to the minus t over tau, where tau is the decay constant defined as simply the product of the resistor in the circuit and the value of the capacitor in farad. So tau is RC. So this relationship is going to be applicable only during the charge cycle, and that's the relationship. T is your time variable, V in is the input voltage, tau is RC. So for example, if you had say over here, I will try to sketch an axis, and let's say I have this going from that, and I am trying to monitor time here, and I'm trying to monitor V out here, and I'm assuming that this is V in. So V in went from 0 to some voltage, say 5 volts. What is going to happen to V out that I'm trying to plot? And I'll try to plot it in red. So V out is not going to change until that particular time, whatever we call this, say T0. Until T0, it will remain the same. And at T0, based on the equation that was derived, that is shown on this slide, the voltage is going to start increasing exponentially. And it will increase like that and asymptotically tend to V in. Actually, it'll become V in. So that's the charging cycle of the capacitor. Now, using this equation, I can derive a very important result that will help us in the 555 timer analysis. So, which is essentially a derivation of a result. So, the next question here is how long does it take for capacitor to charge from, say, VCC divided by 3 to 2 times VCC divided by 3. At this moment, these particular numbers might not make too much sense. VCC is supply voltage, and I'm trying to find out how much time does it take for that capacitor C to charge from 1/3 of that supply voltage to 2/3 of the supply voltage. So if it is, if it is doing this, if this is 1/3 of VCC, and if this is 2/3 of VCC, I'm trying to find out how much time does this take while the charging is happening. Well, to answer this, during the charge cycle, I'm going to look back at the same equation here. Now my V out is going to be 2/3 VCC. Sorry, it has started charging from 1/3 VCC. So V out is going to be 1/3 VCC equals 2/3 VCC times 1 minus e to the negative t over RC. So I'm essentially substituting that for V out and that for V in. So my output voltage has started to increase from 1/3 to 2/3. And if I use this to solve for the time t, let's see, what do I have here? Right. So if I use this to solve for t, then I will get ln2 multiplied by RC. So the time it takes to charge from 1/3 VCC to 2/3 VCC during the charge cycle by solving this particular equation is going to be ln2, which is 0.693 times RC, the value of the resistor through which it charges, and C is the value of the capacitor. So that's the time it's going to take to charge from one start value to the stop value. Okay, so that's a very helpful result. Are we not go? So the question online is, are we not going from 1/3 to 2/3? So why is V out 1/3 VCC? So here, my voltage is going to slowly start increasing. So it is going to start. The V in is essentially my final voltage, right? So if V in is 5 volts, my output will eventually rise to 5 volts. Right now, so that's why V in is a 5 in this case, because my final voltage is 5. In this case, my final voltage is 2/3, so that goes in that spot, and V out is my starting point. Next, if I look at well, that's the charging cycle. Now let's go back and take a look at the discharging cycle. So let me move forward a little bit. Charge done, question answered, new slide. Let's see, discharge cycle. So suppose that we went through that charging of the capacitor for some time, and at a different time we opened the switch. So let's say we had this, the new setup that we are going to look at is simply going to be R and C and connected to ground. So somehow, if we are able to find a way to remove the source from the circuitry by using switches, and only allow the capacitor to be in a loop, in a closed loop, so that current can flow. But in that particular loop, it also has a capacitor. If we set it up this way, then what is going to happen is, because the capacitor has been charged initially, now the source is removed. Now the capacitor is going to discharge through the resistor R. That's the discharge cycle. So clearly the voltage across the capacitor has to go down, right? So what is it going to go down as? Well, it is going to be another exponential, similar tau, so similar decay constant, which is RC, but the voltage at any given time, V out of t is going to be let's say VO, where VO is the initial voltage. So suppose that we charged up the capacitor to VO. In our case, it was 5 volts or 2/3 VCC. So we charge it up to 2/3 VCC or 5 volts or some VO, and then we allowed it to discharge. And as it discharges, the output of the instead of calling it V out, let me call that VC. That's the voltage being measured across the capacitor, VC. So we are monitoring the voltage across the capacitor as a function of time. And the discharge cycle is VO times e to the negative t over tau. Tau is again RC. So if we use this relationship now for the discharge cycle and answer a similar question, how long does it take time to discharge from 2/3 VCC to 1/3 VCC? The answer is going to be related to the same expression over here. So let's see, voltage across the capacitor, initial voltage is 2/3 VCC, and then you have e to the negative t over RC, and voltage across the capacitor can go as low as that. So if you solve this again for time t, you will get the same equation, which is going to be ln2 times RC. So it's 0.693 times RC. So these two are essentially giving us the time it takes to charge from 1/3 VCC to 2/3 VCC, and from 2/3 VCC to 1/3 VCC. VCC is used to denote the supply voltage. And you can use this process for charge and discharge cycle to find out the time to go from any start voltage to stop voltage. So let's see, if I have these two, so I've talked about these two here, let me just highlight the results because these are going to be very useful later on. And that's that. So during the complete analysis, all of these will play a role. Okay, so that's the charging and discharging of the capacitor, and capacitor is a very important element in the 555 and discussion. So let's go on and try to look at the next item. The next item is the internal circuitry of the timer chip. So let's do that by looking at the experiment write-up. So if you look at the experiment write-up, there are essentially two figures over here. The figure D1 on the top has all the external connections being discussed, and figure D2 talks about the inside of the chip. So this is inside of the chip, and this is the external connections. So before I go to the external connections, it is very helpful to look at the internal circuitry. That's what we will do next. So zoom in on this particular figure and let's start talking about how we can analyze this. So to answer the question, what is it doing? So let's see, it is an 8-pin chip. So the 555 timer is a 8-pin chip, which looks very similar to your op amp. Those 8 pins are listed from 1, 2, 3 is the output, 4 is reset, 5 is control voltage, 6 is threshold, 7 is discharge, and 8 is the supply voltage. And you can see we are using VCC to denote the supply voltage. And it could range anywhere from 5 to 15 volts. So any voltage between 5 volts and 15 volts is okay for a 555 timer chip. So pin number 8 is simply connected to VCC, your high voltage. Using waveforms, or sorry, using analog discovery, we will be connecting it to the red wire, the plus 5 volts. and 4 is connected to ground because we are not going to reset it at any time, and 1 is always connected to ground, so we are going to connect that to the black wire. The rest of the remaining wires are going to be useful, and 3 is obviously the output of the chip, where we want that particular free running oscillator to be observed. So let's start this with looking at. I want you guys to look at. Let me highlight this first so that you are looking at the right place. Try to look at this. Just that particular voltage divider. So if you see this over here, you have pin number 8, which is the supply voltage. So let me, as I talk about this, let me draw a schematic here. So that's my DC supply of VCC that is connected to a resistor, a resistor, a resistor, and a ground. So there are 3 resistors that are connected in series with that voltage supply. This is my VCC, and each of these is R, so equal voltage, and we can set this to 5 inside the chip. They are 5K, 5K, 5K. I hope you now see the name 555 timer, because those 3 resistors are 5K, 5K, 5K. And we are interested in monitoring the voltage P1 and P2. P1 is after one resistor, so that's going to be right here, and I can show you that right there. And P2 is going to be in at the junction of the next resistor. So using our voltage divider rule, we know that if you have resistors in series and you apply one particular voltage across all of them, then the voltage gets divided between those resistors proportional to their resistance itself. So P1, based on that logic, what would be P1? What would be the voltage across P1? Well, that particular voltage will be 2 resistors. So let me highlight P1 there. P1 is right there, and P2 is right there. Well, what is P2? Let's answer P2 first. So P2 is going to be the voltage across one resistor, one 5 kilo ohm resistor, which is essentially going to be 1/3 of VCC. Because in the numerator it will be 5K, in the denominator it will be the sum of all 3 of them, so 15K, which will be 1/3 of the supply voltage. In the same manner, if you look at P1, P1 is going to be the voltage across 2 resistors, 1 and 2, to reach to ground. So P1 should be written as 2/3 VCC. Now, I hope that this discussion relates to why we chose those particular voltages in the previous analysis. We, we chose exactly these 2 voltages to answer the charge time and discharge time in the previous example. And that's the reason why, because we are splitting it up into 3 portions, and we are using P1 to be the reference voltage for a comparator here, and P2 for a different comparator here. Those are the 2 references. So I hope that is clear now. So VCC, P1, P2, and essentially ground. Let me, once that is clear, let me erase this and erase this part. I don't need that right now. And I can go in and write for P1, I need 2/3 VCC. and for P2 I need 1/3 VCC. Where is the clock? The question on the online is, where is the clock pin for the flip flop? That clock pin is not being shown over here. The, we are we are not toggling the flip flop using the so we are here is the deal. The inputs of J and K are being controlled by the comparators. So there is a clock input to this flip flop which is uh, not being shown because it doesn't play a role over here. We are going to assume that that particular clock is repeating at a fast rate, much faster than any other thing that changes over here. So if you're trying to use that to do anything, the only the flip flop is, so if you assume that the clock is say 100 hertz and all the other things in this are much slower than that, then for the flip flop and for the output, it doesn't even matter if it is 100 hertz or 200 hertz or 1 kilohertz. So it is one particular frequency that is internal, that is not being shown on this diagram because it doesn't play a role. What plays a role are the comparators. And so the op amp based comparators in the transistor. Okay, so let's see. I have uh, P1 and P2. That's set. That is not going to change with time. Those two voltage are set. And we talked about the three resistors being in the voltage divider configuration. Following that, we have two comparators. So comparators using the op amps, we know what each of them does because we have explored comparators in experiment 6. So for example, if I just want to look at maybe the threshold comparator, I can write some statements over here regarding that. So let's see if I can do that for the comparator. And I'm taking a look at the threshold comparator here. So what happens is I have two inputs to that comparator. One is fixed, which is the 2/3 VCC, and the other is whatever I connect to pin 6. So I'll call that V6. So we could have two situations over here. V6 could be greater than that, or V6 could be less than 2/3 VCC because we are trying to compare it. If V6 is greater than 2/3 VCC, then this voltage is greater than this, so the output saturates high. So you have output which is essentially going into the K input here. So K here is set to 1. Similarly, for the other comparator, you can say uh, what are we comparing? We are comparing voltage on pin 2 and 1/3 VCC. So you could have this greater or less than 1/3 VCC. So if V2 is greater than 1/3 VCC, then you are going to have J, which is what it is feeding into, to be 0. And if it is less, then J is going to be 1. I didn't write this. So V6 is greater than 2/3 VCC, you are going to have K1. If it is less, you are going to have K0. So that's my comparator, threshold comparator, and the trigger comparator analysis statements. So let's see. I may have a situation in which I have both of them 0, 0, which means I'm in the store state, both of them being in 1, 1, which means that I'm in the toggle state, one of them being in a 0 and the other one being in a 1, which means the set as a reset state. So there are all four possibilities over here depending on how I compare these voltages. So and we know what the output Q should look like in those cases because we have looked at the JK flip-flop. Moving on, the well, let's do this. Let's assume that our voltage is uh, greater than 2/3 VCC. So you see what happens over here. If your threshold voltage is greater than 2/3 VCC, what is going to happen? You are going to get a 1 here, which means you could have a reset or a toggle happen. So let's assume that it is resetting here. If it resets, this goes to 0, that goes to 1. And if that goes to 1, that essentially turns on the transistor. And if it turns on the transistor, what is going to happen? Pin 7 is going to be connected directly to ground. And if I were to use pin 7 to discharge the capacitor, then depending on whether the transistor is on or off, I may discharge it or I may not be able to discharge it. In this case, K, when K is 1, we are in the reset state and Q bar becomes a 1, turns the transistor on and allows a capacitor to discharge. The moment the capacitor starts discharging, its voltage will start dropping. So that's how we are going to use that. And note that particular capacitor voltage again will be compared with 1/3 VCC. And if it drops below 1/3 VCC, J will be set to 1, which means Q will go to 1, Q bar will go to 0, and then it will turn off the transistor, which means it will not allow a capacitor to discharge. So what I'm trying to do is I'm trying to make sure that my output goes 0 1 0 1 0 1. However, it does that 0 1 0 1 0 1 in accordance with the voltage of a capacitor that I have not shown inside the chip. It is actually connected to outside the chip. So let's see, there is a question online. Is this when Q is 1 or Q naught is 1? So let's see. Let me write this in this. So now let's suppose it was greater than VCC. If I say threshold voltage is greater than 2/3 VCC, then I have a 1 over here, which means Q bar is 1, turns on the transistor and starts discharging the capacitor. In the other case, if it starts discharging the capacitor voltage will start dropping. And the moment it drops below 1/3 VCC, looks what happens. So if it goes below 1/3 VCC, then you have a 1 over here based on our analysis. That will make this guy a 1 and this guy a 0. That means that it will turn off the transistor, which means the capacitor can no longer discharge. So I'm writing two things over here. One is when the voltage across a certain capacitor is greater than 2/3 VCC and less than 1/3 VCC. So now we have talked about the transistor over here. Transistor over here simply discharges a capacitor. So 7 could be connected to ground directly or could not be connected to anything, which means that it is not allowing the capacitor to discharge. So questions about the internal circuitry of the IC. What are these comparators comparing? What is the JK flip-flop doing? And what is the role of this transistor? So the role of transistor to discharge a capacitor or not. JK flip-flop to go from one set state to reset state depending on what the comparators output. P1 fixed voltage, 2/3 VCC. P2, fixed voltage, 1/3 VCC. And pin 2 and 6 are some input voltages. We are calling it threshold and trigger input voltage that could change over time. Questions about the internal circuitry of the 555? The control voltage is not going to the control, we are not we are not changing the control voltage for the astable mode. We will change the control voltage for this in project 4. So right now we are just simply going to take pin 5 and connect it to a ground with a very tiny capacitor, so it's not playing a role in this analysis. Let's see here. Next we move on to the external connections being made to the 555. So the thing that we saw, all of it was inside this chip 555. Now whatever is connected to outside that chip is going to control for how much time the output is on and for how much time it is off. And I hope you see that particular factor here, 0.693, 0.693, which is essentially natural log of 2, which we saw in our charging and discharging of the capacitor, the time it takes to go from 1/3 VCC to 2/3 VCC and back down. That's why that factor is there, 0.693. Okay, so let's talk about what happens here. So to talk about the external circuitry over here, let me start with the charging cycle. So the capacitor of interest is C1, and as you can see, pin 6 and pin 2, they are both connected to the same pin, same point. So they are both the same, and they are essentially monitoring the voltage of the capacitor. So pin 6 and pin 2 are essentially monitoring voltage across capacitor C1. That's it. So it could go up, it could go down. 5 is a control pin which is connected through a very small capacitor, in this case 0.01 microfarad to ground. 1 is connected to ground. 4 and 8 are connected to VCC, which could be in the range of 5 to 15 volts. We will be using 5 for our analog discovery. R1 is a resistor of my choice. R2 is a resistor of my choice. Pin 7, the discharge pin, is between R1 and R2. So let's say I am in the charging cycle. So let's say I'm charging. And that could happen if, say, voltage across the capacitor initially, if it is 0, and I start my timer, what is going to happen? This voltage that I provide, 5 volts or whatever that is, VCC, that voltage is going to charge my capacitor, C1. So VCC charges C1. And as you can see, it is charging C1 through two resistors that are in series, R1 and R2. Remember, pin 7 over here is not playing a role because it is right now connected to nothing. The transistor is off because the voltage is less than 1/3 VCC. Pin number 2 and pin number 6 are voltage across the capacitor. I said we are assuming that it is 0, so it is less than 1/3 VCC. So transistor is off, pin 7 is connected to nothing here. It's a dangling wire at this point. So the circuit essentially looks like this. You have VCC, you have R1, you have R2, and you have capacitor C1. This is VCC. So what is going to happen? Well, capacitor C1 is going to start charging. What is the charging based on? Well, it is based on the V in 1 minus e to the minus t over tau. What is tau in this case? Well, it is R1 RC. What is R in this case? Well, it is R1 plus R2. What is C? It is simply C1. So the capacitor is going to charge based on this equation with the decay constant between being R1 plus R2. So for how long will it charge? Well, until it hits 2/3 VCC. Because once it hits the voltage across the capacitor, VC, if it reaches 2/3 VCC, it is going to be a turning point. Because right at that moment, pin 7 will be connected to ground and the voltage VCC will be out of the picture and the capacitor will start discharging to ground. So it will start dropping at that time. How does it discharge? Let's see. Discharge. Will it discharge through both resistors? No. Well, you see, if pin 7 is connected to ground here, if this guy is connected to ground, then the circuit is very simple here. You have C1, then just R2, and they are connected to ground. So in this case, it will be Vc e to the negative t over tau, where tau here is R2 times C1. So the decay constant or the time constant for the charging cycle is R1 plus R2 times C1. However, for the discharge, it discharges only through R2, so tau is R2 times C1. Until what time can it discharge? It can only discharge until the voltage across the capacitor drops to 1/3 VCC. Because at that particular time, when it goes below 1/3 VCC, pin number 7 is no longer going to be connected to ground, which means that now the capacitor will start charging again. So if we just try to sketch the voltage across pin 6 and pin 2, they are both the same. If we try to sketch them, how will it look like? Well, if I just take a look at voltage across capacitor, which is essentially monitored by pin 6 and pin 2. They are both the same in this case. What is going to happen? Well, you have, let's say, a time axis over here, and let's say your VCC is 9 volts, for example. So what is going to happen? At the beginning, the voltage across the capacitor is 0, say. It will start charging, and if it is 9 volts, let's see, if this is 9 volts, what is 2/3 VCC? Well, 2/3 VCC is going to be 6 volts, and 1/3 VCC is going to be 3 volts, assuming that VCC is 9 volts. 3 and 6. So initially, if I assume that there is 0 across the capacitor, is going to charge up. Let's say this is 3 and this is 6. Is going to charge up to 6 volts, and exactly at that point we are going to have discharge cycle come in. It will discharge to 3, charge to 6, discharge to 3, charge to 6, and this cycle keeps going on. And we know how much time it takes to go from 2/3 VCC to 1/3 VCC, and we have also found out what is the time it takes to go from 1/3 VCC to 2/3 VCC in a previous calculation. So that is essentially your on time, and this is essentially your off time. Off time is when Q is 0, the output of the timer is 0. On time is when the output of the timer is uh, 1. So on time, we saw the factor 0.693, which is log 2, natural log 2. And during the on cycle, during the charging cycle, what is the time constant? We said 0.693 times RC in the previous discussion. In this case, there is no R and C. There is R1 and R2 and C1. So for on, it is going to be R1 plus R2 times C1. For off, it is going to be 0.693 times R2 times C1. That will allow you to generate an output that looks like this. During the on cycle, it will be 1. So let's say 5 volts is over here. Let me draw another one here. So you go high, low, high, low, high, low. So 0, 5, 0, 5, 0, 5. If this is on time and this is off time, this is Q, the output of the timer. This is time. So we have generated, this is also time. We have generated a square wave, and we did that by simply using a constant power supply, 9 volts. So that's what the fascinating aspect of this 555 timer is. You are able to generate a voltage that changes with time, an AC signal, a square wave, but we only have as an input something that it doesn't change with time, 9 volts, fixed. Now, if you know the on time and the off time, so of course you can find out a few things from this. So for example, how would you find out total time period? Well, if, if you have on time and off time and on time and off time, then if this is T on and this is T off, then the total time period will be the sum of T on and T off. And the frequency of that square wave will be 1 over the time period. So 1 over T on plus T off. How about the duty cycle? Duty cycle expressed as a percentage will be equal to the it is the percentage of the time for which it is on. So it is going to be T on divided by T on plus T off, time percentage of the time for which it is on, as expressed as a percentage. And because we know the expressions for T on and T off, this will essentially simplify to R1 plus R2 divided by R1 plus 2R2. By substituting the expressions for T on and T off that we just talked about over here. Next, an interesting question over here is, can duty cycle be less than 50%? So by using any value of R1 and R2, can you achieve a duty cycle less than 50%? The answer is no, you cannot. You can only get from 50% all the way to close to 100%. So you can only get a duty cycle where your on time is slightly more than the off time, which means to get 20%, what do you do? Well, you generate 80% and then use an inverter. You get 20% duty cycle. So feed the output of the timer chip into an inverter to achieve a duty cycle between 0 and 50%. All right, so all these equations that I have listed over here, they're all detailed over right there. They are just written by the side of the over here. T1 and T2 is being used. I have used T on and T off. So that's those are the principles that govern the 555 timer. Essentially, a capacitor that goes up and down, charges, discharges, and you see that happening. You're trying to monitor that voltage. Okay, so let me stop the video here and then take your question.